Hi, in today's video, we're going to be looking at the competition between E1 versus SN1 versus E2 versus SN2. In some cases, many of these reactions are possible. And so let's first look at the way to evaluate this. I think the best way to do this is to look at a big table. And so on our x-axis, along the top, we're going to look at different types of carbon-halogen bonds. So you have a methyl carbon-halogen or carbon-leaving group bond. You have a primary, a secondary, and a tertiary carbon. So these are the four types that we're going to talk about. In our y-axis, we're going to be talking about whether something is basic or nucleophilic. And I'm using these smiley faces to mean it is a good or a strong base or a good or a strong nucleophile. And so again, in this top left corner, we have a good base and a good nucleophile. So let's start off by looking at the methyl halogen substrates. So methyl, because it cannot do an elimination reaction, because there's only one carbon, either a base or a nucleophile, or that is a molecule that could be basic or nucleophilic, will give you an SN2 reaction. The same is true for something that is basic but not a great nucleophile. So if any reaction is going to occur, it would be SN2. That's why I've drawn the SN2 a little bit smaller, and maybe that reaction will be slower because there's going to be some sort of steric component for that. Now, if there's a molecule that's not a good base but is a good nucleophile, that's absolutely going to do an SN2 reaction. And finally, under these conditions, you're going to observe no reaction. So these are conditions similar to water. We'll talk about that in a few moments. Let's go to the other extreme and go to tertiary compounds. And so these are often going to be very hindered but have the ability to generate carbocations. So when you have a molecule when you're treating that with a molecule that is both basic and nucleophilic, it's going to act as a base, and it's going to give you an E2 elimination reaction. Similarly, when you have something that is basic and not nucleophilic, so a non-nucleophilic base like T-butoxide, that is also going to give you an elimination reaction. When you have a molecule that is not basic but is a decent nucleophile, you'll likely not have any reaction occur at all because, again, this is really hindered toward nucleophilic attack. And finally, if you have a situation where the molecule is neither basic or nucleophilic, you are likely going to undergo an SN1 or an E1 process. And again, when you have an SN1 and E1 process, you're forming that carbocation, and you can't really discriminate which of the two is going to be forming. So let's look along this bottom row a little bit more. And so if you have now a primary carbon under these conditions that are going to generate carbocations, you're likely not going to have a reaction occur because primary carbocations are really unstable. Once you get to the secondary carbocation formation, and for reasons that you can look at in the carbocation stability video, you see that you can form the carbocation, and again, SN1 or E1 processes can occur. Now, if you look to the situation where you have a strong base and a poor nucleophile, so a non-nucleophilic base, with compounds that can do elimination reactions, so primary and secondary, those are both going to be expected to do E2 elimination reactions. Similarly, if you go to a primary or secondary carbocation with something that is a good nucleophile but a weak base, and you can look at the other video to see what scenarios those are, you're going to have an SN2 reaction with the primary carbon. You'll also have an SN2 reaction with the secondary, but it's likely to be pretty slow because you do start to have steric hindrance there, making it difficult for the nucleophile to approach the antibonding orbital of the carbon to X bond. So you can watch the mechanism of SN2 to see why that's the case. And finally, when we're at this top row where you have a molecule that is a good base and a good nucleophile, so that's something like hydroxide or methoxide, now you have challenges when you're looking at a primary versus a secondary. So in the case of a primary, you can expect that an SN2 reaction will occur, but an E2 will also occur, or could also occur. Similarly, on a secondary, the SN2 is going to be a little bit less likely to occur because of steric hindrance, similar argument to down here, but an E2 elimination reaction is going to start to dominate the reaction as the major product. So something I'll highlight is that these top three rows, these are all the conditions you would look for in a reaction. They're typically going to be done in polar aprotic solvents, often DMSO, DMF, THF, or acetone. We've talked about that in a previous video. And this very last row here, these are going to be polar protic solvents like water or methanol, and they are often done under heated conditions. Finally, the last thing that we'll look at in terms of trying to predict which type of reaction is occurring is that these top three rows are generally in basic solutions. So you often, if you were going to do this and check the pH of a solution, it would be on the basic side. And generally, when you're undergoing this SN1/E1 chemistry, those are going to be under acidic conditions. Keep in mind that H plus is an acid, and in these scenarios, you are forming positively charged carbocations, and those are going to be more stabilized under acidic conditions. Well, that's it for this large table. There's a lot to digest. Go ahead and rewatch this video a couple times and try to be able to work out this table by yourself and work through the logic of why each of these boxes is filled in each different way. Again, I recommend going to the extremes first and then filling in the middle using your logic. Thank you for your time and enjoy the rest of your day.